Welcome to this educational video on the field model of graviton activation. Today, we're going to explore an interesting theoretical model in advanced physics that attempts to explain the nature of gravity through the interaction between gravitons and an auxiliary field. Let's start with the fundamentals of this field model of graviton activation. Before we dive into the equations, let's briefly discuss what gravitons are supposed to be in conventional quantum gravity. In standard quantum field theory approaches to gravity, gravitons are hypothetical elementary particles that mediate the force of gravity, similar to how photons mediate the electromagnetic force. However, there are significant challenges with the standard graviton theory. For example, it's difficult to explain why gravity is so much weaker than the other fundamental forces, and attempts to quantize gravity lead to mathematical problems. The field model of graviton activation proposes a different approach. Instead of gravitons directly mediating gravity, this model suggests that gravitons exist, but they need to be activated through interaction with an auxiliary field, which we denote as chi. In this model, the auxiliary field chi acts as a mediator between gravitons and matter, allowing gravity to emerge as a cooperative interaction. Now, let's examine the mathematical formulation of this model. The first key equation is box h mu nu equals -1/m times chi times t mu nu. This equation describes how the graviton field h mu nu responds to the presence of matter. Here, box is the D'Alembert operator, essentially a relativistic version of the Laplacian. T mu nu is the energy-momentum tensor, which represents the distribution of energy and momentum from matter. Notice that chi appears as a multiplicative factor with the energy-momentum tensor. This means that the graviton field h mu nu is not directly sourced by matter alone, but by matter modulated by the auxiliary field chi. Without chi, the gravitons would not respond to the presence of matter. The second fundamental equation is box chi plus v prime of chi equals 1/m times h mu nu t mu nu. This equation completes the coupled system by describing how chi itself evolves. The chi field is governed by its own dynamical equation, which includes a potential term v prime of chi, and most importantly, a source term involving both the graviton field h mu nu and the energy-momentum tensor. This creates a two-way coupling. Chi activates gravitons, and the graviton field, when interacting with matter, feeds back to influence chi. This cooperative interaction is the essence of how gravity emerges in this model. Now, let's explore the physical implications of this model. First, this model suggests that gravitons exist, but they are essentially useless until they are unlocked by interaction with the chi field. This explains why we don't directly observe gravitons in the way we might observe other force carriers like photons. Second, gravity arises only from the cooperative interaction between the graviton field, the chi field, and matter. It's not just gravitons alone mediating the force. Third, this model could potentially explain why gravity is weak compared to other fundamental forces. The weakness could be attributed to the indirect nature of the interaction, requiring the chi field as an intermediary. Let's investigate further implications of this model. This model naturally explains why gravity scales with mass. Since the energy-momentum tensor T mu nu appears in both equations, and this tensor is directly related to the mass and energy distribution of matter, we can see how the gravitational interaction maintains its proportionality to mass. Additionally, this framework hints at possible new physics in the dark sector. The auxiliary field chi could potentially interact with dark matter in ways that differ from its interaction with ordinary matter, offering a new perspective on dark matter and dark energy phenomena. To better understand the significance of this model, let's compare it with standard approaches to gravity. In standard general relativity, gravity is described purely geometrically, where mass and energy directly curve spacetime. In quantum approaches, gravitons directly mediate the gravitational force. In contrast, this field model introduces an additional layer of complexity with the chi field, creating an indirect mechanism for gravity that requires the cooperation of multiple fields. This indirect mechanism could potentially resolve some of the theoretical issues that arise when trying to unify quantum mechanics and gravity. It's worth noting the mathematical consistency of this model. The two coupled equations we've examined form a closed system that respects key physical principles. First, they maintain conservation of energy and momentum. Second, they respect Lorentz covariance, meaning they're compatible with special relativity. Third, There's a gauge invariance associated with the graviton field that's preserved in this formulation. To conclude, the field model of graviton activation provides an intriguing alternative perspective on the nature of gravity by proposing an auxiliary field chi that activates gravitons and mediates their interaction with matter. This model offers potential explanations for several puzzling aspects of gravity: its weakness relative to other forces, its scaling with mass, and challenges in quantum gravity. While this remains a theoretical framework that would require experimental validation, it represents an interesting approach to some of the most fundamental questions in physics, potentially offering new insights into gravity, quantum theory, and the dark sector. Thank you for watching this exploration of the field model of graviton activation. I hope this helped you understand this fascinating theoretical approach to gravity.